Hello students, I am Manoj Kundare, the Assistant Professor of Electronic Science. Welcome back to our e-learning platform. In previous video, we have seen the concept of direct sequence spread spectrum technology. The link of the previous video is available in the description box. Please check it. Now, in this video, we are going to see the concept of the media access control or MAC. In any broadcast network, the key issue is how to determine who gets to use the channel when there is a competition for it. That means in a broadcast network means whenever there are more transmitters and receivers are placed on a single network, then this type of network is known as broadcasting network. Okay, and in this network the main issue is that there is only one channel, and the problem is occurs when that all these stations want to transmit data or receive data through this channel. If all the stations transmits or receives data on at the same time, then the collision occurs. Okay, hence, there is the competition for the use of the channel in broadcast network. To make this point, consider a conference call in which 6 people on 6 different telephones are connected so that each one can hear and talk to all others. Consider a concept here. For example, the 6 people, for example, person A, person B, person C, person D, person E, and person F are all on the conference call. Okay, these all persons are on a conference call. Then each one can hear and talk with other 5 people. For example, A can hear and talk with the other 5 peoples like B, C, D, E, and F. Okay, it is very likely that when one of them stops talking, two or more will start talking at once, leading to chaos. That means here, if A is talking and if A stops the speaking, then it may be possible that B and D talks at the same time, or C and E talks at the same time. That means there is a chow appears. Okay, I hope you all understand the concept here. Let's see once again. If consider the situation where the 6 peoples on a conference call. Okay, the 6 peoples on a conference call. Consider these are the 6 people A, B, C, D, E, F, and these all are a conference call. I hope you all know that what is conference call. Okay, and the situation is that all the connected peoples should or hear and talk with the other peoples. Suppose that A is talking, then after completion of talking, or if A stops talking, then it may be possible that B and C can speak at the same time, or D and E can speak at the same time. Due to this, the chow may appear. Okay, I hope you all now understand the concept. Now consider the next situation in face-to-face meeting. The chow is avoided by external means. For example, at a meeting, people raise their hands to request the permission to speak. Okay, that means in face-to-face meeting, the people raise their hands. Here the diagram shows, or the image shows, this is the meeting and the people raise their hands to request the permission of speak. Okay, now when only a single channel is available, it is much harder to determine who should go next. The protocol used to determine who goes next on a multi-access channel belong to a sublayer of a data link layer called the MAC, or Media Access Control sublayer. The MAC sublayer is especially important in LANs and particularly wireless ones because wireless is a naturally broadcast network. That means generally the MAC address or the media access control protocol is used for the wireless connections. Okay. Now, let's see the further details about the media access control. For that purpose, we have to understand the multiple access communication. The multiple access schemes are used to allow many users to share simultaneously a finite amount of radio spectrum, resources or channel. Okay, that means in multiple access communication, multiple users can use a channel for their communication. Okay, the multiple access protocols is divided into mainly three types: random access protocols, controlled access protocols, and channelization protocol. The random access protocols further divided into four types: ALOHA, CSMA, CSMA CD, and CSMA CA. The controlled access protocol further divided into three types: reservation, polling, and token passing, while the channelization protocols also divided into three types: FDMA, TDMA, CDMA. Let's see the details about each one by one. First of all, let's see the random access protocols. In random access protocols, all the communication stations have the same superiority. That means there is no priority defined between the communicating stations. Okay, that means in random access protocols, all the stations have the same priority. Okay, there is no fixed time or sequence for sending the data between communication stations. Each station has the right to the medium without being controlled by any other stations in random access method. Hence, in random access protocol, any station can send the data depending upon the status of the medium, whether it is available or busy. That means in random access protocol, if the medium is available, then any station can transmit or receive the data. There is no priority is defined between the stations. There are four types of random access protocols, which are ALOHA, CSMA, CSMA-CA, and CSMA-CD. Let's first see what is meant by ALOHA. Okay. ALOHA was developed at the University of Hawaii in early 1970s to connect the computers situated on a different Hawaiian islands. The computers of the ALOHA network transmit on the same radio channel where whenever they have packet to transmit. ALOHA is called as the father of multiple access protocols. Let's see once again. ALOHA is the father of multiple access protocols. There are mainly two types of ALOHA. First one is pure ALOHA and second is slotted ALOHA. The pure ALOHA networking allows the stations to transmit the data at any time, whereas slotted ALOHA protocols allows the station to transmit the data only the beginning of the time. That means in pure ALOHA, we can transmit the data at any instant of time, and in slotted ALOHA, we can transmit the data during the proper slots of the time or at the beginning of the time. Okay, let's see the details about the pure ALOHA. It allows the station to transmit the data at any time whenever they want. After transmitting the data packet, station waits for some time. Then the following two cases are possible. That means here the situation is that the stations are transmitting the data on a channel. Okay, then what happens here, if this station where one has the data, then it transmit it and waits for some time. Then there may be the two cases are appear. The case first is transmitting stations receives an acknowledgement from the receiving station. In this case, transmitting stations assume that the transmission is successful. That means if suppose these are the transmitting stations first, see here, these are the transmitting stations, station first, station second and station third, and this transmitting station want to transmit the data towards the receiving stations A, B and C, and consider the station 1 has the data, then it transmit the data through the channel towards the receiver A. If A transmit the data packet, then it waits for some time. Okay. Then if A transmit the acknowledgement to the one that the data is received successfully, then one consider that the transmission is successful. Okay. I hope you all understand this concept. Then the case second is that the transmission station does not receive an acknowledgement within the specified time from the receiving station. In this case, the transmission station assumes that the transmission is unsuccessful. That means if the transmitting station a gives or a transmission station has the acknowledgement of the transmitting data, then it may be considered as the transmission is successful, and if it does not have the acknowledgement, then it may be considered as the transmission is unsuccessful or fails. Okay. Then what happens? The transmitting station uses the backup strategy and waits for some random amount of time. After backup time, it transmits the data packets again. It keeps trying to until the backup time limit is reached, after which it aborts the transmission. Okay, that means let's consider once again, if there are three transmitting stations 1, 2, 3, and these transmitting stations want to transmit the data towards A, B or C, or it may be possible that one want to transmit the data towards 2 or towards 3. It may be possible, but consider the simple situation here. One transmit to data A, B or C, any of them, okay, through a channel, through a, suppose this is the channel. Then what happens here? A1 transmit the data through the channel towards A. If the transmission is successful, then A gives the acknowledgement to the one. Then in this case we can say that the transmission is successful. But if one or A does not give the acknowledgement to the one, if A does not give the acknowledgement to the transmitter 1, then it may be considered that the transmission is not successful. Hence, at the same time, in this case, the one waits for some time and transmits the data again. Okay, I hope now you all understand the procedure in pure ALOHA. The figure shows an example of frame collision in pure ALOHA. In this figure, there are four stations that contended with one another for access to share a channel. That means there are four stations: station 1, station 2, station 3 and station 4. All these stations are transmitting frames. Okay, these stations are transmits the frames. Some of these frames collide because of multiple frames are in the contention for the shared channel. Only two frames, frame 1.1 and from 1 frame 2.2 survive. All other frames are destroyed. That means in this diagram we can see here that in this diagram we can see here that the station 1, 2, 3 and 4 transmits the frames. Okay, but here we can see that the frame 1.2 and frame 2.1, frame 3.1, frame 4.1 are collide here. Okay, here also frame 1.3 and frame 3.2 is collide here. Only frame 1.1 and from frame 2.2 is survived. Okay, I hope you all understand the collision here. Whenever two frames try to occupy the channel at the same time, there will be collision and both will be damaged. That means here in this part, all the four frames are occupying the same channel and these all four frames are destroyed here. If first bit of the new frame overlaps with the just last bit of the frame almost finished, both the frames will be totally destroyed and both will have to be retransmitted. Okay. If more than one transmitting stations have this problem, then the communication fails in ALOHA. Let's see. In pure ALOHA, each station waits for random time before resending its frame. After timeout period passes to avoid the collision. We call this time as the back of time or TB. That means all the stations in pure ALOHA waits for some random time, and if the transmission is not successful, then it waits for some time. This time is known as the back of time and it is calculated by k is equal to k plus 1. Okay, where k is the number of attempts to send the data, whereas k max is maximum number of attempts allowed for the stations to resend the data. Here k max has the value 15. Okay, that means we can transmit the data, the same data 15 times. Okay, the time for propagation of transmission is TP and time required to send one frame is TFR. Okay, now let's see the explanation about this flowchart. A station which has the frame ready will send it. Okay, that means a station which has a frame ready will send it. If the station has the frame ready, then it send it. Okay, for k equal to 0, that means attempt 0, then it waits for some time t into TP. Okay, then after this time, if it receives the acknowledgement, then transmission is successful. That means it waits for acknowledgement. If it receives the acknowledgement, the transmission is successful. That means this path is follows. Okay, and if the otherwise the station uses the backup strategy. That means if the acknowledgement is not received, then it goes through a backup strategy and it sends the packet again. Okay, the backup strategy is shown here, in which we can see here that the station waits for some backup time which is calculated by k is equal to k plus 1 time. Okay, and if k is greater than k max, then it aborts the operation, and if k is less than k max, then it goes for the next cycle. Okay, after many times k is equal to 15, if there is no acknowledgement, then the stations aborts the idea of the transmission. Okay, the vulnerable time is the time during which no transmission should be done to avoid any collision. That means in pure ALOHA, the vulnerable time is the time during which no transmission should be done to avoid any collision. The vulnerable time in pure ALOHA is 2 into TFR. Throughput is defined as the amount of information or material passed, put through, or delivered in specific period of time. If G is average number of frames generated by the system during one frame transmission, then the maximum throughput or Smax is equal to 0.184, or we can write it as 80.4% for G is equal to 1. Okay, I hope you all understand the pure ALOHA. Now let's see the explanation about the slotted ALOHA. The slotted ALOHA reduces the number of collisions and doubles the capacity of pure ALOHA. The shared channel is divided into a number of discrete time intervals called slots. A station can transmit only at the beginning of each slot, where in pure Aloha, the station can transmit at any instant of time. This is the main basic difference between pure Aloha and the slotted Aloha. However, there can still be collisions if more than one station tries to transmit at the beginning of the same time slot. Okay, here is the diagram for the slotted Aloha is shown. The stations can send the frame only at the beginning of the slot and only one frame is sent in each slot. In slotted Aloha, if the station is not able to place the frame onto the channel at the beginning of the time slot, then it misses the time slot, then the station has to wait until the beginning of the next time slot. That means in this diagram we can see here that there are four stations, station 1, 2, 3 and 4. If the station 2 fails to transmit the data in the first time slot, then it should have to wait for the next time slot. Okay, that means it can send its data through the next time slot. Okay, I hope you all understand the concept here. In slotted Aloha, there is a still possibility of collision if two stations try to send the beginning of the same time slot as shown in the figure. That means here in this time slot, the station 1 and the station 3 transmits the frame on the same channel, hence there is a collision occurs. Similarly, here the collision occurs between station 3rd and station 4th. Okay, slotted Aloha still has an edge over pure Aloha as a chance of collision are reduced to 1/2. The maximum throughput for slotted Aloha Smax is 0.368 for G is equal to or G is equal to 1, or we can write this value into percentage as 36.8%. Okay, I hope you all understand the concept of slotted Aloha here. Now let's see the difference between pure Aloha and slotted Aloha. In pure Aloha, any station can transmit the data at any time. In slotted Aloha, any station can transmit the data at the beginning of any time slot. In pure Aloha, the time is continuous and not globally synchronized, while in slotted Aloha, the time is discrete and globally synchronized. In pure Aloha, vulnerable time in which the collision may occur is equal to 2 into Tt. The vulnerable time in slotted Aloha in which the collision may occur is equal to Tt. Probability in pure Aloha, probability of successful transmission of data packet is equal to G into e raised to minus 2g, where in slotted Aloha, probability of successful transmission of data packet is equal to G into e raised to minus g. The maximum efficiency in pure Aloha is 18.4% and the maximum efficiency in slotted Aloha is 36.8%. The main advantage of pure Aloha is its simplicity in implementation, and the main advantage of slotted Aloha is that it reduces the number of collisions to half and doubles the efficiency of the pure Aloha. Okay, these are the basic differences between pure Aloha and slotted Aloha. I hope you all understand the concept of Aloha. Thank you.